All right, let's just jump right into it. Think about a modern energy well. We're talking about a hole that goes straight down into the earth for a solid mile. But then, almost impossibly, it turns a full 90 degrees and just keeps going, running totally horizontal for another mile and a half.
Which brings up a pretty mind-bending question. How in the world do you steer a drill bit that you literally cannot see from 2 whole miles away through solid rock? You know, there's no steering wheel down there. There's no mechanical linkage turning the bit left or right like the wheels on your car.
Well, the answer is actually shockingly simple, and it comes down to a tiny, tiny number. Just 1.5 degrees. Seriously, the entire steering system for this massive, multi-million-dollar, 2-mile deep operation, it's just a piece of pipe about 2 feet long with a barely noticeable bend of maybe 1.5 degrees.
In the industry, this is called a bent sub. Now, sub is really just drilling slang for a short connector. So it's a short, thick, cylindrical piece of steel with a deliberate, precisely machined bend right in the middle, usually somewhere between 0.5 degree and 3 degrees. Its entire purpose in life is just to point the drill bit slightly off the main axis of the hole. It's this intentional, sacrificial piece of the drill stem.
Now, here is the absolute magic of the bent sub. It's totally counterintuitive, but the exact same tool steers the well in a curve and drills dead straight. It all depends on what the crew does up at the surface. If you hold the entire drill string still and let only the mud motor down below turn the bit, well, that bend stays pointed in one specific direction, right? So the hole carves a curve that way. Drillers call this sliding. But, and here's the genius part, if you rotate the entire drill string from the surface, that little bend sweeps around in a tight circle. It's constantly pointing in all directions, which averages the bend out to 0. The result? The hole drills perfectly straight. One tool, 2 modes, controlled entirely from miles above.
Okay, to really picture this, think about a shopping trolley with one wheel that's slightly crooked. You know the feeling. If you push that trolley straight down the aisle, it stubbornly veers off to one side. Super annoying when you're just trying to buy groceries. But imagine if you could intentionally choose which way that crooked wheel pointed. You'd have a perfect, steerable curve. That's exactly what the bent sub is doing when it's sliding. And just like that trolley, if you were to somehow spin the whole cart around and around as you pushed it forward, the crooked wheel's pull would completely cancel out, and you'd move in a straight overall line.
So how does all this fit together underground? If we build the bottom hole assembly, or BHA, from the bottom up, you start with the bit itself. Then comes the downhole mud motor. And right there, immediately above the motor, is the bent sub. Above that sits the MWD, the measurement wall drilling tool, which acts as the eyes, telling the surface crew exactly which way that bend is pointing. Finally, you have the heavy drill collars. The secret sauce here is the placement. Keeping that bent sub as close to the bit as humanly possible is what allows the driller to make those sharp, aggressive turns. And that tiny tool's placement, that is what makes modern energy production possible on a massive scale. That little 1.5 degree bend is the exact reason a single offshore platform can sit in one spot and drill 20 separate wells, fanning out in 20 completely different directions like an octopus. It's what lets drillers turn a well entirely sideways to thread the needle through a layer of shale rock that might only be 100 feet thick and stay inside it for 2 continuous miles. So put yourself in the driller's boots for a second. You've just finished sliding, you built your 90-degree curve perfectly, now you just need to drill 300 feet dead straight ahead. What do? Do you pull the bent sub out? Like, do you really haul out 2 miles of heavy steel pipe just to remove that one little crooked piece? Absolutely not. You don't trip it out, you just rotate. See, pulling all that pipe out of a well, a process called tripping, burns something like 12 to 24 hours of rig time. That's incredibly expensive. Instead, thanks to that dual mode nature we talked about earlier, the driller just starts rotating the entire drill string. The steering effect instantly averages to 0, and you get a straight hole basically for free. Switching from carving a curve to drilling straight costs absolutely nothing in time or money. But you can't just crank the wheel as hard as you want. You have to be super careful with how sharply you turn. And this brings us to the physical limits of steering, measured by something called dogleg severity. It's exactly what it sounds like, a measurement of how many degrees the hole turns for every 100 feet you drill. A standard directional well builds its curve at a rate of maybe 2 to 4 degrees per 100 feet. If you drop in a sub with a bigger bend angle, or if you just drill a bit slower, that dogleg severity shoots up, and your turn gets much, much sharper. And drillers absolutely obsess over this number, for good reason. There are catastrophic, cascading dangers to a really sharp dogleg. Think about it. Every single joint of rigid steel pipe that goes into that well later on has to flex to get through that curve. If you push the severity too far and try to force straight, rigid steel through a curve that's just too tight, terrible things happen. You get fatigue cracking at the tool joints, the steel casing you run later might literally get stuck and refuse to pass through. And even years down the road, you're going to see excessive wear on the rods or tubing, which inevitably cuts the entire producing life of the well short.
Which really brings us to this profound reality of directional drilling. A bend of just 1.5 degrees looks utterly trivial when it's just sitting there on a rack at the surface. But downhole, it creates a permanent physical geometry that the well has to live with forever. Over thousands and thousands of feet, that one tiny angle dictates whether you hit your target perfectly or miss it completely. It really makes you wonder, doesn't it? How many other multi-million-dollar operations out there are entirely dependent on a single, invisible 1.5-degree variable? Thanks for tuning into this explainer. I hope it helped you visualize the incredible engineering happening a couple miles beneath our feet.